Hi everyone. So today I'll talk about momentum and what momentum means in physics. So momentum is a word that we use in everyday life when we want to say something is hard to stop. Like a team has a momentum, so it just keeps going and it's hard to beat them, right? So this is what essentially in physics, we mean the same thing when we say something has a momentum, which means that it's hard to stop the motion of that thing. So if something is hard to be stopped, it's either very big, it's very massive, it's hard for us to stop it, or it has a very large velocity, so it's going very fast. So that's why, it's hard to stop it. Hence, we say, well, that thing has momentum. Therefore, momentum, which is denoted by P, is mass times velocity. Now, since velocity is a vector, it makes momentum a vector because it's just mass times the velocity, which gives rise to momentum. So if this is a vector, mass times a vector, better be a vector, right? So either something is very big, has a big momentum, or if something is very large in velocity, has a big momentum. In everyday life, it's not like we always have, specific velocity that we go with. We change our velocity, we make U-turns on our way and all that sort of stuff. So this velocity changes all the time. Now, what happens when this ever happens? So if I change my velocity, if I get a change in velocity, I get a change in momentum, as you can see. So I have momentum as m times v. Now, change in velocity gives rise to change in momentum. Now, change in velocity by now should look very familiar to you all. Change in velocity over some time gives rise to acceleration, right? The definition for acceleration was change in velocity over some time. So when you see change in velocity here in this formula, it should remind you of acceleration. Well, if I divide it by t, so let's divide both sides by t so that everything holds correct, then I end up with acceleration here. So now let's rewrite this formula once again and see what comes out of it. So we have delta p over t, we have m times a, right? M times acceleration. Instead of change in velocity versus time, I just wrote acceleration. Now, change in momentum over some time gives me m times a. Now, this should be really familiar to you. What is m times a? Is the net force, right? So net force is essentially mass times acceleration. That's pretty cool. So let's rewrite everything once again. Okay, so change in momentum over some time is essentially the net force acting on the body. So suppose something is moving, it has some mass, it's moving with velocity of v. I know it has some momentum. Now the velocity changes to some other number. So it gets, let's say it gets bigger. My second velocity is bigger than my first one, but the same object, right? So if P1 is this, now P2, the second momentum is mv2, and I know this is different from that just because now velocity is it's literally two times bigger than v1, as you can see from the length of the vectors. So change in momentum gives rise to, basically change in velocity gives rise to change in momentum. And now if I measure this change during some time, let's say this change is happening in 5 seconds. So during some time. So if this change happens during some time, this is essentially acceleration, m times a is essentially net force, and I end up with change in momentum versus that 5 seconds, that the time over which this change happened, and that gives rise to the net force. So let's see what physically what we mean by the net force. It means something was throwing this way, like pushing it that way so that its velocity changed. If it would be a car, then it would be the acceleration due to me pressing on the gas pedal that gave rise to the speedometer number change, on like the number that changes on the speedometer. So that would be that pushing force of my foot on the gas pedal that gives rise to this F net, which means the acceleration times the mass of the car, which gives rise to the change in velocity, which again gives rise to the change in momentum. See how things are hold together very beautifully. So whenever you are having a change in your velocity, you know that there has to be some net force exerting on your system. Otherwise, due to Newton's first law, if you're not exerting any force on your system, the velocity never changes. It stays the same at all times, as long as there is no net force acting on it. However, when you are pushing it, pulling it, do something to it, whenever this comes into play, the net force, some resultant force comes into play and affects your motion, then your velocity has to change. That was the definition for acceleration, and acceleration and force, I told you they are linked together. So it's a definition of acceleration, which definition of acceleration is change in velocity. Whenever that ever happens, there has to be some net force acting on your system. Otherwise, if there is zero net force, then it should, go with the velocity of constant, right? So that's that. Let's just do a little bit of manipulation on this formula, knowing that, well, if this changes, there is this net force acting on my system. So delta P over T gives me net force. Now let's multiply both sides by a T to get rid of this T here. So delta P, if I want to isolate this, then delta P is net force times time. So let's just box this and take a moment and see what's inside this box. Inside this box, on the one hand, we are having change in momentum, which means change in the velocity. So it was like going by this, and then it changes the velocity, so the momentum changes. So this part tells me change in momentum. This part tells me the net force that gives rise to this change of momentum multiplied by the time over which this change happens. This is called impulse. Impulse is essentially change in momentum in something. Or in another way, net force on something multiplied by the time over which the force acts on something. Both of them are impulse, depending on the question and depending on the information you're given in the question. If in the question you're giving about the mass and velocities of things and you're asked about impulse, go it this way. If in the question you're asked about force and and times and things like that, and you're asked about impulse, then go this way. Right? So these are both impulses. Now, I told you, if maybe 2-3 minutes ago, I said, well, if there is a net force acting on something, I know the net force gives rise to some change in velocity, which means acceleration, and that's the whole thing. This is the formula. But now, if there is no net force on something, due to Newton's third law, if there is no net force on something, it has to go with the constant velocity forever. But let's see if the formula says the same thing. I set net force to 0. Then delta P becomes 0 times T, and that is 0, which means no change. That's exactly that, right? delta P becomes 0. Delta P is 0, which means no change in momentum, which means no change in velocity of the object, which means the velocity is constant, right? So constant velocity when F net is 0. And we know this from Newton's first law anyways. So these are like different ways of explaining the same thing, and namely explaining the motion of a particle. In the next video, I'll talk about more about momentum. Bye-bye.